Hold out your hand. Look at it resting there, solid, familiar, undeniable. You see skin, ridges of fingerprints, maybe a faint pulse beating in the wrist. To your eyes, it is a certainty, matter, mass, flesh. But let us fall inward. Beneath the skin, a lattice of cells. Beneath the cells, molecules. Beneath the molecules, atoms, each a miniature solar system of orbiting electrons. Deeper still, the nucleus, dense with protons and neutrons. And deeper still, beyond the nucleus, beyond the atom, beyond what you can ever hope to see, the hadrons. They are everywhere. Every proton you've ever heard of, every neutron that makes up the atomic heart, every fleeting particle born in the chaos of a collider, all are hadrons. Your body is made almost entirely of them. The stars overhead, the ground beneath your feet, the air in your lungs. All of it rests on their existence. In truth, if hadrons did not endure, neither would you. They are the bricks upon which reality builds its cathedral. And yet, here is the provocation. Are hadrons even real? It sounds absurd, doesn't it? These particles are measured, categorized, their effects undeniable. They scatter in detectors, leave tracks in chambers, ripple the screens of our machines. We can calculate their masses, their lifetimes, their decays. They are as real as anything in physics. But the closer we look, the more this certainty erodes. Hadrons are not fundamental. They are not indivisible. They are not stable in the way we once imagined. Instead, they are turbulent, emergent, their very identity dissolving under scrutiny. What does it mean to call them real when they are storms of smaller entities, patterns that flicker and vanish, held together not by permanence but by ceaseless struggle? This is the paradox at the heart of our journey. To most, the world feels solid, but physics has taught us that solidity is an illusion. At the deepest level, matter is restless, shifting, and strange. And nowhere is this more evident than in the hadrons.
The story of hadrons is the story of the universe's attempt at order. In the early 20th century, the discovery of dozens, then hundreds of new particles threatened to overwhelm our understanding. They poured out of accelerators like an endless zoo: protons, neutrons, pions, kaons, lambdas, sigmas, deltas, omegas. A chaotic menagerie, each with its own mass, charge, and decay path. It was bewildering. Where was the simplicity? Where was the unity? Had nature betrayed us, replacing the dream of order with the nightmare of excess? And then came the revelation. These particles were not unique species, but variations on a theme. Like notes on a scale, they belonged to families, organized by hidden rules. And at the core of this revelation was the idea that hadrons were not fundamental at all. They were composites built from quarks and bound by gluons. What seemed like a zoo was in fact a pattern. But this revelation also raised the unsettling possibility that hadrons were illusions, not fundamental, not indivisible, not the real building blocks we had hoped for. So what then are hadrons? Are they real in themselves? Or are they masks worn by deeper truths? Are they the bedrock of matter, or shadows cast by quarks and gluons? To answer this, we must walk a path both scientific and philosophical, tracing their discovery, their contradictions, and their deeper meanings. And make no mistake, this is not an idle curiosity. The reality of hadrons defines the reality of you. When you hold out your hand, you are holding hadrons. If they are not real, then what does that say about your hand, about your body, about the world? The stakes, then, are nothing less than the definition of reality itself. To begin this journey, we must start in the ordinary world, the world before the revelation. A world where matter seemed simple, where atoms were the final answer, where protons and neutrons were indivisible. This was the illusion that comforted us, the illusion that gave us a sense of solidity. But it was an illusion soon to be shattered. For beneath the ordinary world of atoms lies the extraordinary world of hadrons, a world of storm and flux, of hidden quarks and restless gluons, of particles that flicker in and out of being.
To ask if hadrons are real is to ask if anything we call solid can truly be trusted. It is to question the ground we stand upon. And so we begin, not with answers, but with a question that refuses to let go. What if the very particles that make up your body, the stars, and the universe itself are not what they seem? The hand on the table feels solid, but solidity is a lie. Inside, hadrons churn. Inside, reality falters. Inside, the greatest mystery of all waits to be unveiled. And so, the journey begins. There is a moment, early in every great story, when someone, often quietly, almost as if in passing, speaks the truth that will define everything to come. In cinema, it is the theme stated. In life, it is the unsettling question that keeps you awake at night. For us, on this journey into the strange, shifting world of hadrons, that question is deceptively simple. What does it mean to be real? To call something real is to anchor it in existence, to declare it more than illusion. A rock in your hand is real, the sunlight warming your face is real, the ticking of a clock is real, but physics is crueler to our intuitions. Time, as Einstein showed us, bends and stretches. Light behaves as both wave and particle. Matter itself dissolves into fields and probabilities, and at the center of this unraveling, the hadron stands as both foundation and enigma. When scientists first named these particles hadrons, they were drawing from the Greek word hadros, meaning thick or strong. The name fit. These were the heavyweights of matter, the particles bound by the strong nuclear force, the most powerful force in the known universe. Hadrons were meant to be the anchors of physics, the bulwarks against uncertainty. Protons and neutrons together formed the nucleus. The nucleus formed the atom. Atoms formed molecules. Molecules formed everything we know. What could be more real? And yet that word, hadros, strong, masked a deeper fragility. Protons, once thought eternal, are now suspected to decay over spans of time so vast they make stars seem young. Neutrons, stable inside a nucleus, crumble into protons, electrons and neutrinos when left alone. Pions, kaons, and the rest of the hadronic zoo exist only for instants, flickers of reality that die as quickly as they are born. The supposedly thick particles are, in truth, more like ripples, disturbances in a deeper medium. So we ask again, what does it mean to be real? If reality is measured in permanence, then hadrons fail. If reality is measured in indivisibility, they fail again. And yet, without them, nothing exists. The contradiction is profound. Hadrons are simultaneously essential and elusive, omnipresent and unstable, the very foundation of matter and yet built from smaller, hidden things. They occupy a space that philosophy has long recognized, the space between essence and appearance. Are they real in themselves, or are they masks worn by quarks and gluons? This is the theme of our story, the reality of hadrons, and by extension, the reality of matter itself. But themes in great narratives are never presented cleanly. They arrive as tension, as paradox, as a question that refuses to resolve. The hadrons embody this perfectly. Consider the proton, the most familiar hadron of all. It lives inside every atom, a constant companion of your body and your world, but try to describe it precisely and it becomes slippery. What is its mass? Scientists have argued over decimal places for decades. What is its radius? Experiments disagree. Does it decay? We do not know. Even the question of what a proton is leads to confusion. Is it a bag of 3 quarks? A sea of quark-antiquark pairs? A storm of gluons? The answer depends on when you look, how you look, and what theory you believe. The proton, solid foundation of all matter, is like a shadow on a cave wall, undeniable, yet elusive.
And so the theme sharpens. Perhaps reality is not what endures, but what persists in appearance. Perhaps reality is not essence, but effect. If protons hold the world together, then they are real in the most pragmatic sense, even if their identities dissolve under scrutiny. But if reality is supposed to mean something absolute, something final, then hadrons trouble us. They force us to admit that what we call real may always be provisional, always subject to deeper truths.
This is not new to philosophy. Plato's allegory of the cave warned us that shadows might deceive. Kant taught that the thing in itself is beyond our perception. The hadrons are their modern heirs, whispering that the particles we see are not things, but phenomena, not bedrock, but ripples. And yet there is another possibility, more unsettling still. What if hadrons are not less real, but more real? What if their messy, emergent nature is not a failure, but a lesson? Reality may not lie in permanence or simplicity, but in complexity, in flux, in the dance of forces. In this view, the proton is not an illusion, but a triumph, a self-organized knot of energy that persists across billions of years, not because it is simple, but because it is intricate. This possibility turns our question inside out. Instead of asking whether hadrons are real enough, we begin to ask whether we are capable of recognizing reality when it is presented as storm rather than stone. That is the heart of this documentary and of this journey. Hadrons are more than particles. They are philosophical provocations. They force us to confront the meaning of reality itself. Are we willing to accept that reality is turbulent? Are we willing to accept that what endures is not permanence, but ceaseless transformation? As with all great stories, the theme stated is a seed. It will not blossom immediately. For now, it lingers as a question, but it is a question that will guide us, whether we acknowledge it or not. And so, as our narrative unfolds, remember this. When you hear the word hadron, do not picture a simple particle. Picture a paradox. Picture a storm. Picture a reality that is real only because it refuses to stay still. The theme has been stated. The question has been asked. What does it mean to be real? The rest of our journey will attempt an answer. But first, as in all great myths, the call to adventure awaits. And so we step forward, leaving the comfort of assumptions behind, into a world where the very particles of existence dissolve under our gaze. The hadrons are calling. Will we listen? Every story must begin with a sense of stability, with an ordinary world that feels solid enough to stand upon, so that when it collapses, the fall shocks us into transformation. In the tale of hadrons, that ordinary world was the mid-20th century, an era when physics seemed poised to unify the universe with clean, elegant simplicity. The atom had been split, the nucleus probed, the proton and neutron identified as the building blocks of all matter. To most scientists of the 1940s and 1950s, the story appeared nearly complete. The nucleus was made of protons and neutrons. Electrons orbited beyond. Together, these three particles seemed to explain everything, from the solidity of a stone to the life beating in a heart. A tidy trinity, elegant and final. Textbooks proclaimed it with confidence. The proton and neutron were indivisible, fundamental, the cornerstones of the material world. But nature is never so easily caged. The deeper physicists looked, the stranger the world became. It began with cosmic rays, those high-energy messengers from space that smashed into Earth's atmosphere, showering detectors with unfamiliar tracks. New particles appeared, some heavy, some fleeting, none fitting neatly into the proton-neutron-electron model. Mesons, strange baryons, resonances, all emerging like ghosts from collisions. Physicists began to joke, half in wonder, half in despair, that their once tidy world was turning into a particle zoo. At first, each new discovery was greeted with celebration. A new meson here, a new baryon there. But as the list grew, excitement soured into confusion. By the 1960s, dozens of particles had been catalogued, then hundreds. Each had its own name, its own mass, its own fleeting lifetime. Some were stable enough to linger, others decayed in millionths of a second. The zoo grew crowded, chaotic, and incomprehensible. The ordinary world of physics cracked under the weight of its own abundance. What had begun as a story of simplicity, the proton and neutron as indivisible atoms of the nucleus, was collapsing into disorder. The question loomed: was this chaos a fundamental truth, or was there some hidden order beneath it? The hadrons were at the center of the storm. Hadron became the catch-all label for these heavy, strongly interacting particles. Protons and neutrons were hadrons, yes, but so too were the mesons, the kaons, the lambdas, the deltas, and countless others. Each seemed unique, yet all were bound by the same inscrutable force, the strong interaction, the invisible glue that kept the nucleus from tearing itself apart. The strong force itself only deepened the mystery. Gravity was weak but universal, shaping stars and galaxies. Electromagnetism governed light and electricity. The weak force triggered radioactivity. These forces had their place, predictable and calculable. But the strong force was different. It was overwhelming in its intensity, yet confined to the tiniest scales. It bound protons and neutrons so tightly that separating them seemed impossible. In fact, no one had ever seen a free quark, or anything smaller within a proton. Hadrons seemed indivisible not because they were simple, but because they were prisoners of an unimaginably strong bond. This was the ordinary world of hadron physics as the 20th century entered its most fevered decades, a zoo of particles, an incomprehensible abundance, a force that defied intuition. The neat world of three particles had become a labyrinth of hundreds, and yet within that chaos lay a deeper beauty, one waiting to be revealed. Patterns began to emerge. Just as Mendeleev once saw order in the periodic table of elements, physicists began to suspect that the hadronic zoo was not random. Certain particles seemed to group together, sharing properties, decaying in predictable ways. These patterns hinted at an unseen structure, a hidden architecture beneath the surface. Murray Gell-Mann, a physicist with a mind attuned to symmetry, gave this suspicion its form. He proposed the eightfold way, a classification scheme that arranged hadrons into elegant families, mirroring the mathematical symmetries of group theory. It was as if the zoo, once chaotic, had suddenly been organized into constellations. Each family had its place, each particle fit into a greater design. The eightfold way was more than bookkeeping. It was prophecy. The gaps in the scheme predicted particles not yet discovered. And when experiments revealed these missing members, particles like the omega minus, exactly where the pattern said it must be, the prophecy was fulfilled. Suddenly, the Hadron Zoo was no longer chaos, but an echo of something deeper. Yet even this was not the end. Gell-Mann and independently George Zweig took the next step. What if hadrons were not fundamental at all? What if they were composites, made of even smaller entities? They gave these hypothetical entities a name: quarks. At first the idea seemed absurd. Quarks carried fractional charges, values no one had ever observed. They had never been seen directly. Many physicists resisted, clinging to the idea of hadrons as indivisible. But as experiments grew more precise, the evidence mounted. Deep inelastic scattering at Stanford revealed substructure within the proton, scattering patterns that could only be explained if smaller constituents were rattling inside. The quark model was born. The hadrons, once thought fundamental, were now seen as composites, bound states of quarks and gluons. Protons and neutrons became three quark systems. Mesons became quark-antiquark pairs. The zoo dissolved into order. And yet, the irony was profound. By explaining hadrons in terms of quarks, physics had both simplified and complicated reality. Simplified because hundreds of particles could now be explained as combinations of just a handful of quarks. Complicated because the strong force, mediated by gluons, was unlike anything else in nature. So strong it confined quarks forever, ensuring that no quark could ever escape alone. This was the ordinary world shattered and remade. The hadrons were no longer the indivisible building blocks of matter, but the battleground where quarks and gluons played out the drama of the strong force. They were not ends, but intermediaries, storm systems of energy and motion, fleeting arrangements in a deeper, invisible sea. For our story, this is the setup. The world we enter is one where hadrons appear ordinary, stable protons, familiar neutrons, the particles of everyday matter. But beneath that surface lies a history of chaos, discovery, resistance, and revelation. The hadron is not simple, it is not indivisible, it is not permanent. It is instead a clue, a signpost pointing us toward the deeper reality of quarks, gluons, and the strange rules of confinement. This is the world as it stands, the ordinary world of our narrative. And like all ordinary worlds in great stories, it is about to be disrupted. The hadrons are not what we thought, they never were, and the truth that awaits us will force us to question not only the particles themselves, but the very meaning of reality. The stage is set. The call to adventure is coming. Will we dare to follow? Every great journey needs a rupture, a moment when the ordinary world can no longer contain itself, when the ground underfoot shifts so violently that denial becomes impossible. In the saga of hadrons, that moment came not as a single explosion, but as a series of shocks, data points, collisions, anomalies that shattered the illusion of simplicity and propelled physics into uncharted territory. For decades, the hadron was thought indivisible. The proton and neutron were bedrocks. They carried mass, they held the nucleus together, they defined matter itself. But as accelerators grew larger, and beams of electrons were hurled at protons with ever-increasing energy, the first cracks began to appear. The year was 1968, at the Stanford Linear Accelerator Center in California. A beam of electrons, accelerated to unimaginable speeds, was fired directly into protons. What should have happened, if protons were truly indivisible, was predictable. The electrons would scatter in a manner consistent with smooth, solid spheres, bouncing off without revealing any deeper structure. Instead, something stranger emerged. The scattering patterns were jagged, discontinuous, inexplicable if protons were solid particles. It was as though the electrons had struck something inside the proton, smaller entities hidden within. The data suggested that protons contained point-like constituents, much smaller than themselves. These constituents would later be identified as quarks. It was a moment of rupture. The proton had cracked open, its supposed indivisibility exposed as myth. The news rippled through the physics world like a thunderclap. For some, it was confirmation of what Gell-Mann and Zweig had already theorized. Quarks were real. For others, it was deeply unsettling. If protons and neutrons were made of smaller parts, then the hadrons were not fundamental at all. They were composites, cages of unimaginable energy binding quarks so tightly they could never escape. The catalyst had arrived. Hadrons were no longer the endpoint of matter. They were storm systems, containers, illusions masking something deeper. And yet, even this revelation was incomplete. Because what the experiments revealed was not simply the presence of quarks, but the presence of a force, something holding them in place, something more powerful than anything else in nature, a force that refused to let quarks escape, a force that grew stronger the further quarks tried to separate. This force came to be known as the strong interaction carried by gluons. Here lies the paradox that catalyzed the crisis. The very evidence that proved quarks existed also proved that quarks could never be seen directly. They were forever confined within hadrons, bound by gluons in a dance of eternal imprisonment. Unlike electrons, which roam freely, quarks are hidden, masked, locked behind an impenetrable wall. The hadron was both a revelation and a prison. This contradiction tore at the foundations of physics. On the one hand, the quark model explained the zoo of particles, reduced hundreds of hadrons to a handful of combinations. On the other hand, it introduced a force so bizarre it defied analogy. A force where freedom existed only at the smallest distances, where quarks behaved almost independently when close together, but were chained irreversibly when they tried to escape. This was asymptotic freedom and infrared slavery, terms as poetic as they were terrifying. The catalyst was not simply the discovery of quarks. It was the realization that hadrons themselves were illusions, shells concealing a storm that could never be observed directly. The implications reverberated far beyond particle physics. For centuries, humanity had pursued the dream of fundamental building blocks, atoms, indivisible units, final truths. Each time we thought we had reached the bottom, the ground gave way again. The atoms split into electrons and nuclei, the nucleus split into protons and neutrons, and now protons and neutrons split into quarks and gluons. But here the descent met a wall. Quarks were never free. They were permanent prisoners. The very idea of fundamental reality seemed to slip away. This was the moment that forced physicists to reimagine the meaning of matter. Were hadrons real in the way we once thought? Or were they only manifestations, fleeting arrangements of deeper fields and forces? The catalyst pushed the field into chaos and opportunity. Experimentalists raced to probe deeper, smashing particles together at higher energies, searching for hints of quark liberation. Theorists labored to craft equations that could describe the bizarre behavior of the strong force. Out of this crucible, quantum chromodynamics, QCD, was born, a theory as elegant as it was daunting, describing the interplay of quarks and gluons with the language of color charge and symmetry. But even as QCD rose, the paradox remained. The very constituents it described could never be observed directly. Quarks were real yet untouchable. Gluons carried force yet remained invisible. Hadrons were the only things we could measure, and yet hadrons were no longer fundamental. They were masks, containers, approximations. This is the essence of the catalyst, the collapse of certainty. The proton was no longer the indivisible bedrock of reality, but a storm of imprisoned quarks. The neutron was no longer a simple matter, but a battleground of gluons binding particles that could never escape. The hadron was no longer a building block, but a stage for an eternal play that no eye could ever see. From here, the story could never return to what it once was. The ordinary world of tidy atoms and indivisible protons had been annihilated. In its place stood a new reality, one where the fundamental was forever hidden, where the visible was only a mask, where matter itself was less certain than myth. This is what drove the next act of the journey, the search not just for particles but for meaning. If hadrons were not truly real, then what was? Were quarks and gluons the ultimate bedrock? Or were they too only another mask, another illusion, another layer hiding something deeper? The catalyst does not answer, it only disrupts, and disruption is enough. Because now the seeker cannot rest. Now the story must move forward into trials, ordeals, and revelations that will test the very meaning of reality itself. And so the journey deepens. If hadrons are illusions, then what truth lies behind the mask? Every great transformation encounters resistance. After the catalyst, there is always a pause, a lingering uncertainty, a struggle between clinging to the old world and stepping into the new. For hadrons, that pause took the form of doubt, controversy, and fierce debate. If quarks were real, if hadrons were no longer indivisible, then everything we thought we knew about matter was undone. And scientists, for all their devotion to discovery, are also human. They hesitate when the ground shakes too violently. In the 1960s and early 1970s, the particle zoo was still swelling with new arrivals. Mesons, baryons, hyperons, they were catalogued with increasingly complex naming systems. The Eightfold Way had given a glimpse of order, but many physicists were not yet ready to accept the radical leap to quarks. For some, quarks were nothing more than mathematical scaffolding, placeholders to explain the patterns of the zoo. They were convenient, yes, but real. That was another matter. The debate hinged on one profound discomfort. No one had ever seen a quark. Electrons could be isolated, photons could be detected, protons could be captured in bottles, neutrons in reactors. But quarks? Never. They existed only within hadrons, always hidden, never free. To many, this smacked of metaphysics. A particle you could never isolate. Was it even a particle at all? Skeptics sharpened their arguments. They pointed to the fractional charges of quarks, 2/3 and 1/3 the charge of the electron. No instrument had ever measured such values. Why invent particles so bizarre, only to insist they would forever remain unseen? Better, some argued, to stick with hadrons themselves as the true fundamental particles, however messy the zoo became. Others embraced more radical alternatives. Perhaps the zoo was not reducible at all. Perhaps nature was intrinsically complex, its fabric woven from an infinite variety of particles. The search for simplicity, for fundamental building blocks, was itself a human conceit, not a reflection of reality. In this view, hadrons were real, irreducible, and endlessly diverse. But the quark advocates countered with growing evidence. The deep inelastic scattering experiments at Stanford were too precise to ignore. Electrons probing protons did not scatter randomly, as they would if the proton were a featureless sphere. They scattered in patterns that betrayed the presence of smaller, point-like objects inside. These partons, as Richard Feynman called them, looked suspiciously like quarks. Yet even here the debate raged. Were partons and quarks the same thing? Or were they merely mathematical conveniences that happened to produce the right results? Feynman himself, ever the trickster, often described partons in deliberately vague terms, sidestepping the ontological question. He cared less about whether quarks really existed and more about whether the equations worked. But others craved certainty. Reality mattered. The debate grew philosophical as much as scientific. What does it mean for something to be real? Must it be observable, detectable? Or is its necessity within a theory enough to grant it reality? Quarks occupied this grey space, forcing physicists to confront the uneasy boundary between the seen and the inferred. The resistance was not only philosophical, there were technical hurdles too. Quantum chromodynamics, the emerging theory of quarks and gluons, was elegant but notoriously difficult to calculate. Unlike electromagnetism, whose equations could be solved with relative ease, QCD defied straightforward solutions. Its equations were non-linear, tangled, forbiddingly complex. To skeptics, this was further evidence that the quark model was a beautiful illusion, not a workable description of reality. And yet, the cracks in skepticism deepened with every experiment. Proton collisions revealed jets of particles spraying outward in patterns consistent with quark interactions. High-energy collisions showed scaling behaviors that made sense only if quarks were inside. The hadrons themselves, the zoo of baryons and mesons, fit neatly into quark combinations, like letters forming words. 3 quarks made a baryon. A quark and an antiquark made a meson. Suddenly, the chaos of the zoo was grammar. But still, doubt lingered. Some physicists dug in, insisting that until a quark was isolated, its existence remained a hypothesis, not a fact. Others argued that quark confinement was too fantastical, a force that grew stronger as particles moved apart, ensuring quarks would never be free. Such a force seemed backwards, alien to human intuition. Was nature really so perverse? This was the heart of the debate, a clash between intuition and evidence, between the desire for observable proof and the acceptance of theoretical necessity. On one side, the comfort of hadrons as fundamental, messy but visible. On the other, the unsettling beauty of quarks and gluons, mathematically compelling, experimentally supported, but forever hidden. The debate spilled into conferences, papers, and even the culture of physics itself. Some journals hesitated to publish bold claims about quarks. Some senior physicists dismissed the younger generation's enthusiasm as misplaced zeal. The community fractured between believers and skeptics, each armed with their own vision of reality. And in this fracturing, the deeper question emerged: what exactly were hadrons? If they were not fundamental, then what was their status? Were they illusions, emergent phenomena, temporary cages for quarks? Or were they still real in some sense, even if not ultimate? Could something be both composite and fundamental, both illusory and indispensable? The debate forced physicists to wrestle not only with equations, but with ontology. The proton, once the bedrock of matter, was now an arena of doubt. The neutron, once the quiet sibling of the proton, was now a theater of confinement. Mesons, once curiosities, were now essential players in the quark narrative. Every hadron became a question mark. This was the liminal stage of the story, the moment after the catalyst when the hero hesitates, unsure of the path forward. Do we cling to the old world of hadrons as indivisible? Or do we leap into the new world of quarks and gluons, however strange? The debate stretched across years, across conferences and labs, across equations scratched on blackboards late at night. But history has its momentum. The evidence piled higher, the doubts wore thinner, the mathematics grew sharper. The debate could not last forever. Eventually, the tide turned. Quarks became accepted, gluons embraced, QCD elevated as the theory of the strong interaction. Hadrons were redefined, not as the bedrock of reality, but as the prisons of quarks, the manifestations of a deeper hidden truth. Yet something was lost in that acceptance, for even as quarks became real, hadrons slipped into a new kind of unreality. They were no longer the indivisible blocks of matter, but composite shadows, epiphenomena of quark interactions. Their ontological status blurred, uncertain. Were they real? Were they illusions? Or were they something stranger still? A reality born of unreality, a mask that both conceals and reveals. The debate ended not with resolution, but with transformation. Hadrons had changed. Their place in the story had shifted forever. And in that shift, the journey pressed forward toward trials and ordeals that would test not only the theory, but the very limits of human understanding. The hesitation was over. The leap had been made. The debate had set the stage for what was to come. The trials of QCD, the ordeals of confinement, the revelations of symmetry and fields. But in the quiet between debates, one question still lingered. If hadrons are illusions, then what does that make us? Who are made of them? In every story shaped by the save the cat structure, there comes a moment when hesitation ends. The debate, however fierce, cannot last forever. The hero must cross a threshold, must step into the unknown world with no way back. For hadrons, this moment came when the physics community finally accepted the leap, that protons, neutrons, and the zoo of heavy particles were not the bedrock of reality, but the surface froth of something deeper. Quarks and gluons were not convenient fictions. They were the architecture of matter itself. The break into two is never clean, never unanimous, never without pain. It was the 1970s, and the world of particle physics was fracturing and rebuilding itself in real time. The deep, inelastic scattering experiments at Stanford had exposed the internal scaffolding of the proton. The eightfold way had already whispered of hidden order. The quark model was gaining traction. And then came the theory that would cement the transition: quantum chromodynamics. QCD was audacious. Where electromagnetism had Maxwell's equations elegant and linear, QCD offered a jungle of non-linear interactions. Where photons carried the electromagnetic force but never interacted with each other, gluons, the carriers of the strong force, interacted with one another directly, creating a self-reinforcing web of energy and tension. The equations were beautiful, but terrifying. They suggested a world where quarks could never be liberated, where confinement was absolute, where the hadrons we measured were not the thing itself, but the shadows cast by quarks imprisoned within. This was the threshold crossing moment. The old world of hadrons as fundamental particles was abandoned. The new world, stranger, darker, more mathematically elegant, became the only viable path forward. But crossing into this new world required courage. For QCD was not just a new theory, it was a rewriting of reality itself. It declared that everything humanity had called matter, stones, stars, our own bodies, was built not from protons and neutrons, but from quarks, forever hidden, bound by gluons that could never be observed directly. The familiar had dissolved into the unseen. The break was not only scientific but philosophical. To accept QCD was to accept that reality was, at its most fundamental level, inaccessible. We could measure cross-sections, scattering patterns, jets of particles, but never the quarks themselves. We could see their influence, but never their naked form. The hadron was no longer real in the sense of being indivisible. It was real in the sense of being the only thing we could measure. A paradox. The observable was the illusion. The unobservable was the truth. Physicists embraced this paradox with a mix of triumph and unease. On the one hand, QCD unified the chaos of the particle zoo into a coherent framework. Hundreds of hadrons could be explained as quark combinations. Symmetries emerged, predictions matched experiments, and the theory offered astonishing explanatory power. On the other hand, the cost of this unification was unsettling. The acknowledgement that our direct sensory grasp of matter stopped at the walls of confinement. Beyond those walls, reality was forever hidden. This was the world of Act 2, the upside-down world in narrative terms. Having crossed the threshold, the hero enters a landscape governed by new rules, rules that challenge and unsettle. For hadrons, this world was defined by QCD's revelations. One of those revelations was asymptotic freedom. Unlike gravity, which grows stronger as masses come closer, or electromagnetism, which weakens with distance, the strong force behaves perversely. When quarks are pressed tightly together within a hadron, the strong force between them weakens, allowing them to move almost freely. But when quarks try to separate, the force grows stronger, like a rubber band stretched to breaking, but a rubber band that never snaps. This ensured that quarks could never be observed in isolation. Freedom at the smallest scales, eternal imprisonment at the largest. This duality, freedom and confinement, became the defining feature of the new world. It was a world where paradox was not failure, but structure. A world where reality's most powerful force could not be seen, only inferred. A world where the things we touched and measured, protons, neutrons, hadrons, were not ultimate but emergent. The break into two is always unsettling. In myth, it is the crossing from the known village into the dark forest, from the safety of home into the realm of danger and transformation. For physics, it was the crossing from visible particles into invisible dynamics. The forest was QCD itself, tangled, non-linear, and unforgiving. To cross into this forest required new tools. Physicists turned to computers, to lattice QCD, carving space-time into grids and simulating quarks and gluons with raw computational power. They turned to accelerators, smashing particles together at unprecedented energies, looking for signatures of jets that betrayed quark motion. They turned to cosmic rays, to neutron stars, to the early universe where matter itself existed in quark-gluon plasma, a soup of liberated quarks recreated for fractions of a second. Each experiment confirmed the same unsettling truth. Hadrons were not fundamental. They were cages. They were shells. They were the surface patterns of a deeper storm. This was the new reality, the new act, the upside-down world, and in embracing it, physicists crossed a point of no return. But the break into two is not only about science, it is also about us. For if hadrons are not truly real, Then what does that say about our place in the cosmos? Everything tangible, tables, mountains, stars, is made of protons and neutrons, which are themselves not fundamental but masks. The reality we perceive is built from illusions, stabilized by forces we cannot see. Matter is both real and unreal, present and absent, measurable and unknowable. This is the unsettling beauty of Act 2. To accept it is to abandon the comfort of certainty and embrace the paradox of existence. The hadron, once the bedrock of matter, becomes a symbol of hidden depth, a reminder that reality is always stranger than our stories. The leap has been made. The old world of indivisible protons is gone. The new world of quarks and gluons is here, with all its paradox and power, and the journey has only just begun. For once the threshold is crossed, there is no turning back. Only trials remain, ordeals that will test not only the theory, but the very idea of reality itself. The question that lingers is not whether hadrons are real, but how deep the illusion goes. The search for hadrons is not just the story of particles, it is inevitably the story of us. Every time humanity peers deeper into the structure of matter, we do so with more than curiosity. We do it with longing. We want foundations, certainty, an unshakable bedrock upon which to place our questions, and yet, with each descent, the bedrock dissolves into storm. Atoms split into electrons and nuclei. Nuclei split into protons and neutrons. Protons and neutrons dissolve into quarks and gluons. Every answer fractures into further mysteries. This parallel story has always run alongside the physics. It is the human need for permanence in a universe of impermanence. We see it in philosophy, religion, myth. Ancient thinkers searched for elemental substances, earth, air, fire, water, believing that beneath all diversity there must be something simple and indivisible. The Greek atomists gave us atomos, the uncuttable particle. Medieval scholars sought divine order, crystalline spheres that held the stars in place. Always, there has been a hunger for the one thing that cannot be broken. Hadron seemed for a time to answer that hunger. The proton was stable, surviving longer than the universe itself. The neutron, though less eternal, was essential, holding nuclei together. These particles felt permanent, ultimate, beyond question. They gave shape to the ordinary world we touch every day, the solidity of matter beneath our hands. But when quarks were discovered, when gluons were introduced, when QCD declared that protons were not ultimate but cages of confinement, the human hunger for foundations was shaken again. What does it mean if even the bedrock of matter is not fundamental? What if reality itself is always deeper, always hidden, always beyond our grasp? Here lies the parallel story. The physics of hadrons mirrors the human struggle with uncertainty. We want to believe in permanence, but we live in a world of impermanence. We want to hold on to the visible, but we are told that the visible is only a mask. We want to know the truth, but the truth may be that there is no final truth, only deeper layers of illusion. This is not merely philosophy for its own sake, it shapes how we engage with science itself. The debates over quarks were not only about data, they were about belief, about how far we are willing to follow theory into the unseen. Some resisted because they could not accept a reality forever inaccessible. Others embraced it because they were willing to let go of the demand for visibility. The human psyche was as much at stake as the proton. In this way, the story of hadrons becomes a mirror for the story of human knowledge. Each advance forces us to confront the limits of our perception. Each breakthrough demands that we abandon certainties and accept paradox. The hadron, once the foundation of matter, becomes a symbol of impermanence, a reminder that what we take as final is always provisional. And yet, there is another side to this parallel story. For even as quarks and gluons retreat beyond observation, the hadrons remain indispensable. Protons and neutrons still define chemistry, biology, life. They are illusions, yes, but illusions that shape stars and galaxies. They are masks, yes, but masks that make reality what it is. In this way, the hadron occupies a liminal status, not ultimate, not false, but emergent. Real enough to build the universe, unreal enough to hide its foundations. This tension between the real and unreal is deeply human. We too are emergent. We too are illusions shaped by deeper processes, cells, molecules, atoms, particles. Our consciousness itself arises not from anything fundamental, but from networks of neurons, from electrical storms in the brain. The Hadron's paradox is our own, real enough to exist, unreal enough to depend on forces we cannot see. The parallel story also carries a warning. Humanity has always craved certainty, and that craving has often led us astray. We build myths, we cling to dogmas, we resist the unsettling truth of impermanence. The Hadrons remind us that reality is not built to satisfy our desire for foundations, it is built to confound it. To accept this is to grow wiser, more humble, more attuned to the strange beauty of a universe that refuses to stand still. In the laboratories, this humility has become essential. Physicists no longer expect to see quarks or gluons directly. They study scattering patterns, jet structures, lattice calculations, statistical signatures. They learn to read the shadows, to infer the storm from its effects. In doing so, they have embraced a deeper truth. That reality need not be visible to be real, that invisibility itself can be a form of presence. And so the parallel story deepens. The physics of hadrons is not only about particles, it is about learning to live without final answers, about embracing the unseen, about finding meaning in the emergent rather than the fundamental. It is about letting go of the hunger for the indivisible and accepting that the universe is woven from paradox. But even here, the story does not end. For the acceptance of quarks and gluons, of confinement and emergence, only sets the stage for the next ordeal. If hadrons are not ultimate, then what lies beyond them? If protons are cages, then what of the universe built from those cages? If the visible is a mask, then what does the mask conceal? This is where the human and the scientific stories converge, for just as physics moves from ordinary world into ordeal, so too must we confront the deeper implications. The hadron is no longer a bedrock, it is a riddle, and the riddle is only beginning. The parallel story runs with us, whispering in our ear, "You will not find certainty here. You will find only wonder and the humility to stand before mystery." And with that whisper, the journey presses forward. The illusions are stripped away, the ordeals await. The question is no longer simply, are hadrons real? The question becomes, what does real even mean when everything we see dissolves into what we cannot? The deeper we step into the hadron world, the more it feels like a carnival of strangeness. Once, scientists thought there might only be a few fundamental building blocks, electrons, protons, neutrons. But when accelerators smashed matter open in the mid-20th century, the fragments that spilled out were too numerous to count. They weren't just protons and neutrons, they were hundreds of other hadrons, particles that lived briefly, then decayed into showers of lighter ones. Each hadron was a new riddle, a new creature in a zoo that grew more crowded by the month. Physicists called it the particle zoo, and for good reason. Baryons, the family that includes protons and neutrons, turned out to have cousins, the hyperons, built from strange quarks, heavy and unstable. Then came mesons, lighter hadrons made of a quark and an antiquark bound together, the pion, the kaon, the rho, the omega, particles that lived fleeting lives, whispering secrets of the strong force before they vanished into more familiar forms. Every new particle was like a mask pulled from a hidden masquerade. Where once physics seemed simple, it now teemed with variety, complexity, contradiction. For a while, the sheer number of hadrons threatened to overwhelm the dream of order. Were all these particles fundamental? Was reality not built from a few blocks but from hundreds? The beauty of simplicity seemed lost, and yet, behind the chaos, a deeper order lurked. Murray Gell-Mann and George Zweig, with their quark model, revealed that the particle zoo was not a jungle but an orchestra. Each hadron, no matter how exotic, was simply a different arrangement of the same underlying notes, quarks. 3 quarks for baryons, 1 quark and 1 antiquark for mesons. Suddenly the zoo became a pattern. The chaos revealed symmetry. But just as the model brought clarity, it also invited strangeness. For if hadrons were built from quarks, then why stop at 3? Why stop at 2? Couldn't quarks arrange themselves in 4s, in 5s, in combinations never before imagined? The answer was yes, and the search began for exotic hadrons, tetraquarks, pentaquarks, hybrid states with gluons woven into their very structure. At first, these exotic states seemed like fantasies. For decades, physicists hunted for them, only to find shadows, whispers, ambiguous signals. But in recent years, with powerful detectors like those at CERN's Large Hadron Collider, the exotics have stepped into the light. Tetraquarks, particles of 4 quarks bound together. Pentaquarks, 5 quarks interlocked in ephemeral forms. These are not stable building blocks of matter, but fleeting echoes of what quarks can do when pressed together under extreme conditions. Imagine it, quarks not only forming protons and neutrons, but briefly locking into stranger geometries, like dancers forming patterns only to dissolve again. Each exotic hadron is a glimpse into the flexibility of the strong force, into the wild creativity of confinement, and the story grows stranger still. Some mesons may not even be quark-antiquark pairs at all, but bound states of gluons themselves, glue balls, particles made of pure force, without matter inside. Their existence is predicted, their hints tantalizing, but their identities elusive. If confirmed, they would prove that the very glue of the universe can harden into particles of its own. A force becoming matter, a paradox made real. In this way, the hadron world is not only a zoo, but a kaleidoscope. Each collision in an accelerator is like a turn of the glass, rearranging quarks and gluons into new patterns, new symmetries, new fleeting forms. It is as though the universe itself were experimenting, showing us the possibilities hidden within its code. This richness, this strangeness, is the promise of the premise. To ask whether hadrons are real is not to ask whether they are singular and simple. It is to ask whether we can embrace their multiplicity, their fluidity, their paradoxical existence as both stable and unstable, visible and invisible, emergent and fundamental. For protons and neutrons, the familiar baryons, are only the beginning. The hadron world is vast, strange, and endlessly inventive. It teaches us that matter is not a rigid foundation, but a play of possibilities, a canvas where the strong force paints with quarks and gluons in patterns beyond imagination. And with each new discovery, the question deepens. If these strange hadrons exist, what else might? If tetraquarks and glue balls are real, what lies beyond them? Is there a limit to the creativity of the strong force, or are we only scratching the surface of a deeper, wilder symphony? The fun and games of the hadron world are not trivial diversions. They are the universe showing us its hidden repertoire. They remind us that reality is not narrow, but expansive, not rigid, but fluid, not simple, but endlessly complex. The particle zoo may seem chaotic, but it is in that chaos that the deeper order reveals itself. For every strange hadron discovered, every fleeting resonance caught in the data is a reminder that reality itself is stranger than we dare believe. And yet, even here at the height of wonder, shadows loom. For if the hadron world is so rich, why do we only see protons and neutrons in the everyday? Why do the exotics fade so quickly, vanishing into silence? What does it mean that the universe chooses stability only for certain hadrons, leaving the others to flicker and die? That is the riddle that waits as we move forward. The richness of hadrons is dazzling, But behind it lies a question we cannot yet escape. If hadrons are real, why do they feel like illusions, fleeting and fragile, conjured only in the violence of collisions? For a moment it seemed the storm had passed. After decades of chaos, particle after particle tumbling out of accelerators, too many to count, too many to classify, the Standard Model emerged like a lighthouse through the fog. Suddenly, the zoo of hadrons no longer looked like a mess of unrelated beasts, but like a carefully arranged menagerie, each species accounted for, each lineage explained. The revelation was quarks and gluons. 3 quarks make a baryon, a quark and an antiquark form a meson. And gluons, those elusive carriers of the strong force, wove them together, binding them in an invisible net so powerful it refused to break. From this, the chaotic multiplicity of hadrons snapped into focus. What had once been bewildering now felt almost inevitable. And with the Standard Model, the apparent triumph was not just aesthetic, it was empirical. Precision experiments matched the predictions of theory with uncanny accuracy. Collisions at CERN and Fermilab confirmed the lifetimes, the decay channels, the resonance structures that the quark-gluon picture demanded. The deep, inelastic scattering experiments at SLAC in the late 1960s had been the turning point, the moment when physicists looked inside protons and neutrons and found evidence of hard, point-like constituents, quarks, lurking within. It was the smoking gun. From then on, the Standard Model grew not just as a theory, but as a framework capable of absorbing experimental blows and returning with its structure intact. Quantum chromodynamics, QCD, became the jewel in the crown, a theory of the strong force so elegant, so rich, that it seemed to reconcile the contradictions of the particle zoo. Its mathematics revealed confinement, that quarks could never be isolated, that the very act of pulling them apart created more hadrons instead of exposing them naked. It explained asymptotic freedom, that quarks behaved like free particles only at unimaginably high energies, yet bound themselves tighter at low ones. These paradoxes were not flaws but features. They were the very signatures of QCD's strength. In this narrative, hadrons found their place at last. They were not mysterious entities, but the natural consequence of quarks bound by gluons. Protons, neutrons, mesons, all of them emerged as the inevitable orchestra of the strong force. The false victory was intoxicating. For once, the story felt finished. And how could it not? The Standard Model predicted results with a precision no other physical framework in history had ever achieved. The magnetic moments of particles, the rates of decay, the scattering cross-sections, numbers pulled from equations matched the real-world data to astonishing decimal places. It was as though the universe itself had surrendered its secrets, revealing that at its core, it was calculable, predictable, mastered. Yet beneath the applause, cracks remained. For one, no one had ever seen a free quark. The Standard Model explained why, confinement forbade it, but the absence lingered like a ghost. We infer quarks, we model them, we treat them as real, but we cannot isolate them, cannot touch them, cannot hold one in a detector. Do they exist in the same sense as protons and electrons, or are they convenient fictions, mathematical phantoms designed to rescue order from chaos? And then there were the exotics. The Standard Model allowed for them, predicted them in principle, but the evidence was always slippery. Tetraquarks and pentaquarks flickered into view, but their fleeting existence raised questions. Were they truly bound states, or just temporary associations of smaller hadrons clumped together? The Standard Model provided a language, but not clarity. Even the triumph of QCD carried with it a quiet despair. The equations were there, yes, but they were nearly impossible to solve at low energies, in the regime where hadrons actually live. Perturbation theory, the neat trick of expanding around small interactions, failed utterly in the strong coupling of QCD. To know a hadron deeply, to calculate its structure from first principles, required computational brute force, lattice QCD simulations, churning through supercomputer time to approximate what the mathematics stubbornly refused to yield. The solution was not so simple after all. And then came the larger absences. The Standard Model, for all its precision, said nothing about gravity. It could not account for dark matter, that invisible substance outweighing ordinary matter 5 to 1. It could not explain why quarks and leptons came in 3 generations, or why their masses spread across such bizarre ranges. The very existence of the Higgs field, necessary to give particles their mass, felt like a patch, a deus ex machina inserted to make the mathematics hold. Still, in the midpoint of the story, none of this mattered to the optimists. Hadrons were understood, at least enough to silence the chaos. The Standard Model was celebrated as one of humanity's greatest intellectual triumphs, a map of the subatomic world so detailed it bordered on divine. It was a false victory, but it gleamed like a real one. The narrative was seductive. Hadrons are real, they are quark composites, they are bound by gluons, and we understand them. To the uninitiated, it felt like closure. To the physicists, it felt like progress. To history, it felt like triumph. And yet, deep down, an unease lingered. For every experiment that confirmed the Standard Model, there was another that teased at its edges. Muons behaving strangely in magnetic fields, rare decays refusing to line up with predictions, neutrinos oscillating in ways the framework never anticipated, and above it all, the unsettling fact that the universe itself, on the largest scales, seemed to be governed by forces and particles the Standard Model did not even acknowledge. So the hadrons stood as both proof and puzzle. Proof that quarks and gluons, at least as concepts, could tame the zoo. Puzzle because their very existence raised more questions than answers. Were hadrons the final truth of matter, or just another illusion, another step on the ladder toward a deeper structure still concealed? The Standard Model's apparent victory was a midpoint, not because it ended the story, but because it lulled us into thinking the story was finished. The zoo had been ordered, the mathematics aligned, the experiments confirmed. But just beyond the horizon, new questions gathered like thunderclouds, waiting to reveal that the triumph was not final, not complete, not even stable. For now, though, the applause echoed. The zoo had been tamed, the theory triumphant, the hadron world explained. It was a false ending, a false peace, but one that carried with it the seductive dream that perhaps, just perhaps, we had finally grasped reality. But the universe has a way of shattering our illusions. And the next act would prove that the neatness of the Standard Model concealed mysteries far stranger than anyone dared admit. It is often said that every great victory sows the seeds of its own undoing. For the Standard Model, and for hadrons themselves, that seed was doubt. What appeared to be closure began, piece by piece, to fracture under the weight of anomalies, gaps, and the unsettling recognition that what we thought we knew might be little more than the scaffolding of a deeper truth. The Standard Model gave us a neat story. Hadrons are simply collections of quarks, held together by gluons. Baryons, mesons, and their resonances could be charted, catalogued, predicted. But as physicists looked closer, the neatness blurred. The bad guys of the narrative, the contradictions, the unexplained, the specters of missing knowledge, began to close in. Start with confinement. On paper, quarks are the building blocks of hadrons. They carry fractional charges, combine in trios or pairs, and explain the bewildering zoo. But confinement ensures they can never be isolated, never measured directly. Every attempt to smash a proton apart produces not a liberated quark, but a spray of new hadrons, as if the universe itself conspires to keep quarks hidden. We talk about them, we calculate with them, we depend on them, but we cannot touch them. Are they truly real or merely mathematical devices that explain patterns we observe? The heart of hadronic physics is haunted by this question, and no experiment has yet exorcised it. Then there is the problem of exotics. For decades, the Standard Model permitted their existence, but the evidence was slippery. And then, in the early 21st century, came the reports from the Large Hadron Collider and other experiments, tetraquarks, pentaquarks, states that seemed to go beyond the simple quark triplets and quark-antiquark pairs. Suddenly, the menagerie was not quite so neat. Were these truly new forms of matter, or transient clumps held together by chance collisions? Were they evidence of a richer substructure, or simply the natural extension of what we already knew? The answers remain unclear. For each new, exotic discovery, there comes a wave of skepticism. Maybe it's just a statistical fluctuation. Maybe it's an artifact of measurement. Maybe it's not what we think. And beneath even these questions lies the shadow of QCD itself. Quantum chromodynamics is, in principle, a complete theory of the strong force, but in practice, it is nearly impossible to solve. Its equations are elegant, but merciless. At the energies where hadrons exist, the coupling becomes so strong that perturbative methods, the bread and butter of quantum field theory, collapse. To calculate the properties of a proton from first principles requires immense lattice simulations, supercomputers grinding through vast numerical approximations. And even then, the results are approximations, not proofs. We live with the uneasy knowledge that we cannot fully calculate the very objects that are supposed to be the cornerstones of matter. A proton, the stable particle on which the visible universe depends, is, in some sense, still mysterious. And then come the anomalies, the quiet whispers of physics that does not fit the standard model's tidy frame. The magnetic moment of the muon, measured to deviate from theoretical predictions. Rare decays of B mesons that show puzzling asymmetries. Neutrino oscillations that defy the model's silence on neutrino mass. Each of these may be unrelated to hadrons directly, but together they paint a troubling picture. The standard model, for all its success, is incomplete, and if it is incomplete, then hadrons, explained only within its walls, may be less real than we assume. Worse still, there are the cosmic questions. Dark matter does not seem to interact with hadrons, at least not in ways we can detect. Dark energy, that accelerating expansion of the universe, remains wholly beyond the standard model's reach. Even within hadronic physics itself, puzzles remain. Why does the proton have the mass it does? Quark masses alone cannot explain it. The vast majority of a proton's mass arises from the energy of gluon interactions, from the very binding that holds it together. In other words, the proton's substance is not matter at all, but energy trapped in ceaseless motion. That is a profound strangeness. Hadrons, the building blocks of matter, are themselves built not from matter, but from fields and forces in eternal flux. Consider too the proton spin crisis. For decades, physicists assumed that the proton's spin, its intrinsic angular momentum, came directly from the spins of its constituent quarks. Yet experiments revealed a different story. The quark spins account for only a fraction of the total. The rest comes from gluons and orbital angular momentum, contributions far harder to visualize, far stranger to accept. The proton, that most stable of particles, is not a tidy sum of its parts, but a storm of hidden contributions. And what of stability itself? Protons appear eternal, lasting longer than the age of the universe. But many grand unified theories predict proton decay, that even these cornerstones of matter must eventually crumble. If true, then hadrons are not ultimate, not eternal, not final. They are temporary scaffolding in a cosmos whose deepest structure may be stranger still. Experiments continue to search for signs of proton decay in massive underground detectors, but so far, silence reigns. Yet the possibility itself gnaws at our certainty. Each of these puzzles might, in isolation, be a curiosity. Together they form a tightening net. The bad guys close in not as villains with faces but as gaps, contradictions and silences. The standard model explains so much but leaves too much untouched. Hadrons, once the triumph of classification, now stand as symbols of what we do not know. And as if to underscore the unease, the frontier of physics continues to blur the line between particles and illusions. Are hadrons truly distinct entities, or are they emergent phenomena, patterns rising from deeper quantum fields we do not yet understand? Just as temperature is not a thing, but a collective property of atoms in motion, perhaps hadrons too are emergent, real only in the sense that waves on the ocean are real, though no individual water molecule is a wave. This is the tension, the pressure building as the narrative deepens. The false victory of the standard model is exposed for what it is, a fragile order, one that cannot account for the mysteries gathering at its edges. And yet, there is beauty in this tension, for in the very act of confronting what we do not know, we glimpse the possibility of what might be discovered. Every unanswered question about hadrons is a doorway into the unknown. Every anomaly is an invitation to reconsider our assumptions. Every failure of the standard model is a crack through which the light of a deeper theory might shine. The triumph was never final. The zoo is not truly tamed. The hadrons are not so easily explained. And so the story presses forward, haunted by questions, driven by contradictions, propelled by the unsettling recognition that the building blocks of reality may not be what they seem. The bad guys have arrived, not as destroyers, but as reminders, that the deeper we peer into the universe, the less stable our certainties become, and that reality, in its strangeness, resists being contained. The question lingers. If hadrons are not the end of the story, then what are they? Are they truly real, or only shadows of something deeper, something still waiting to be revealed? There is a moment in every grand story when the ground seems to fall away. For hadrons, that moment is now. The triumph of classification, the illusion of mastery, and the confidence of the standard model are all confronted by the one enemy no theory can escape: doubt. It begins not with a dramatic explosion, but with quiet whispers, cracks forming in the very foundation of what we call reality. For the physicists who had once believed that protons and neutrons were the end of the story, solid, eternal, fundamental, the revelations of the past half-century cut like a blade. These particles, far from being stable cornerstones, are storm systems of energy, probabilistic fogs held together by equations that cannot be solved by hand. They are not billiard balls rolling in a cosmic machine. They are not even things in the way we understand things. And once this realization takes hold, the certainty collapses. Take confinement again, that peculiar rule that quarks cannot be isolated. For decades, researchers smashed protons together, hoping to peel out their innards, to glimpse the mythical quark directly. But nature mocked them. Each attempt gave rise not to a liberated quark, but to a shower of new hadrons, as though the very act of asking the question triggered reality to invent new answers. The lesson was unmistakable. Quarks are phantoms. We may calculate with them, rely on their existence in theory, but never touch them. If the quarks are untouchable, then are hadrons themselves truly real, or just mirages conjured by deeper laws? Then comes the crisis of mass. The proton, familiar and dependable, contains 3 valence quarks, whose combined bare masses are but a fraction of the whole. The rest, over 95%, arises not from matter, but from the wild dance of gluons and the kinetic frenzy of quarks zipping around at nearly the speed of light. In other words, the proton's substance is almost entirely energy, locked in ceaseless motion. The most stable particle in the visible universe is not a solid brick, but a storm. What does it mean if the foundation of matter itself is nothing more than perpetual turbulence? Spin deepens the unease. For years, physicists assumed that the proton's spin was the simple sum of its constituent quarks. But when the data arrived, it told a different story. The quarks contribute only a sliver. The rest comes from the swirl of gluons and orbital motion, phenomena impossible to visualize with everyday intuition. It was not just an experimental puzzle, it was an existential one. If even the spin of the proton, that most basic of properties, cannot be traced to its parts, then what does it mean to call a proton real? In the shadow of these crises, exotic states emerged. Tetraquarks, pentaquarks, resonances that blurred the neat taxonomy. Instead of closure, they delivered confusion. What counted as a hadron? Was there a limit to what quarks and gluons could assemble into? Or were we stumbling into a wilderness of bound states we barely understood? With each discovery came doubt, because the very framework for naming these particles seemed provisional, contingent, fragile. The collapse of certainty was not confined to experiment, it seeped into theory as well. Quantum chromodynamics, the proud crown jewel of the strong force, refused to yield its secrets easily. Its equations worked only in the high-energy realm, where perturbative methods applied. But at the scale of protons and neutrons, the very scale that mattered most, the mathematics turned intractable. Supercomputers struggled, approximations abounded, and every calculation felt like peering through fog. The theory we claimed explained hadrons could not, in fact, give us their properties directly. We stood in the strange position of insisting hadrons were real, while admitting we could not calculate their reality from first principles. This tension spread into the cosmos. The universe we inhabit is mostly not made of hadrons at all. Dark matter, dark energy, the vast unseen scaffolding of existence. These account for over 95% of the cosmos, and hadrons are irrelevant to both. Even worse, hadrons may not be eternal. Grand unified theories whisper that protons must eventually decay, leaving nothing behind. Experiments have searched for decades, listening for the faintest sign of a proton's death, but have found only silence. Still, the possibility hangs over us. The supposed bedrock of reality might one day crumble to dust. This is the all-is-lost moment, the nadir of the narrative. The proton, the neutron, the hadron zoo, none of it offers the comfort it once did. They are not immutable bricks, but fragile constructs, emergent phenomena rising from fields and forces we do not truly understand. Our most familiar companions, the particles that form our bodies, our planet, our stars, dissolve under scrutiny into uncertainty, turbulence, and shadows. And the philosophical implications cut deep. If hadrons are emergent, then perhaps reality itself is layered illusion. Just as temperature is not a thing, but a property of countless molecules in motion, perhaps hadrons too are not things, but collective excitations, patterns in the quantum fields that underlie everything. They are real only in the way a wave is real on the surface of the ocean. Not a separate entity, but a behavior, a phenomenon, an echo. In the quiet halls of underground laboratories, in the humming chambers of particle colliders, in the equations etched across chalkboards, the same unease resonates. Have we misunderstood the very idea of matter? Have we mistaken the appearance of solidity for truth? The collapse of certainty is not just scientific, it is existential. For if the hadrons are illusions, then so too are we, our atoms, our flesh, our bones, all of it built from patterns in fields, all of it transient, all of it shadows. To look at a proton and see not a thing but a storm is to realize that reality itself is storm. This is the moment where the narrative breathes darkness, where the story seems to end in despair. The building blocks of the universe dissolve, and nothing remains but questions. But from this abyss, there is also the whisper of possibility. The collapse of certainty is not the end, it is the beginning. For if hadrons are not real in the way we thought, then perhaps reality is richer, deeper, stranger than we ever dared to imagine. The ground has given way, but in falling, we may discover the hidden depths of the universe. The laboratory is quiet now. The roar of colliders, the flashes of detection screens, the elation of discovery, all seem muted. What remains is the silence of doubt, the heavy weight of questions that refuse to be answered. Physicists, once confident in their grasp of hadrons, find themselves pacing corridors, staring at chalkboards covered in half-erased equations, wondering if they have reached the limits of human understanding. This is the dark night of the soul, when science itself seems haunted. The unease begins with the nature of reality. If protons, neutrons, and the whole hadron family are not fundamental but emergent, then what is the true bedrock of the universe? Are quarks and gluons more real, or are they too only convenient fictions, mathematical constructs that describe behavior without being ontological entities? Every theory, every model, every particle seems to dissolve into the same paradox. Real enough to calculate, real enough to measure indirectly, but always out of reach. Reality itself feels like smoke in the hand. Worse still is the problem of scale. Quantum chromodynamics works well in the high-energy realm, where quarks behave like weakly interacting particles. But at the lower energies where hadrons actually exist, the mathematics becomes unsolvable. Even the most advanced supercomputers struggle to simulate the proton with precision. Decades of progress have brought us closer, but never close enough. The very theory we claim explains hadrons fails us at the exact scale where we need it most. It is as though the truth hides in plain sight, locked behind a door we cannot open. The crisis deepens when we look outward toward the cosmos. The visible universe, the stars, the galaxies, the planets, is built from hadrons, but hadrons account for less than 5% of all that exists. Dark matter and dark energy dwarf them, stretching across the cosmos like shadows of a deeper truth. And so the question grows louder. If most of reality is not made of hadrons, then why should we believe in their primacy at all? Are we clinging to a parochial understanding, mistaking the local for the universal, the familiar for the true? The despair is not only scientific, it is human. Generations of physicists have dedicated their lives to the study of hadrons. They have built machines the size of cities, invested careers into deciphering the symmetries of quarks and gluons, written papers that describe particles as though they were pieces of eternity. To discover that these particles may not be fundamental, that their reality may be contingent, is to risk the sense that one's life work has been chasing ghosts. This is the moment of doubt that every seeker of truth must face, the possibility that truth is forever beyond reach. The Greeks once thought atoms were indivisible. Newton thought space and time were absolute. Bohr thought electrons orbited like planets. Every generation believed it had uncovered the bedrock, and every generation was wrong. Are hadrons just the latest illusion? And if so, what comes after? Yet despair itself is a strange kind of teacher. In the silence of failure, a new humility takes root. Physicists begin to ask not just what is real, but what do we mean by real? Is a proton real in the same way a wave is real on the ocean? Is it real like temperature, an emergent property of many hidden motions? Or is it real only in the sense that it gives rise to phenomena we can observe, like atoms and molecules and life itself? This shift is profound. It moves the conversation from physics into philosophy, from equations into ontology. It forces us to confront the possibility that our categories of thought, object, particle, matter, are inadequate for the universe we inhabit. Perhaps the universe is not made of things at all, but of relationships, interactions, patterns in fields. Perhaps hadrons are less objects and more processes, existing not as eternal bricks, but as fleeting dances in the quantum sea. The dark night of the soul stretches on. Experiments search for proton decay and find nothing. Simulations strive for precision and fall short. Exotic particles appear and vanish, like mirages in the desert. Each new clue adds to the weight of uncertainty. The standard model, once hailed as a triumph, now feels like a prison. Complete enough to resist collapse, incomplete enough to resist transcendence. And so physics lingers in this twilight. The old certainties are gone, but the new vision has not yet arrived. The hadron, once the bedrock of existence, now feels like a mask, and beneath it lies a face we cannot yet see. This is the crisis point, when the narrative teeters on the edge of despair. For if hadrons are not what we thought, then what, if anything, is? Yet within this darkness, faint glimmers appear. Lattice QCD, once a blunt tool, begins to sharpen. Detectors become more sensitive, teasing out signals from the noise. Theories grow bolder, reaching beyond the standard model toward unification, toward strings, toward dimensions unseen. The night is long, but it is not eternal. Still, for now, the wait remains. The proton is a storm of energy, the neutron a restless phantom, the hadron zoo a collection of fleeting apparitions. Reality feels fragile, unstable, forever receding. And yet we cannot look away, because in the very collapse of certainty lies the possibility of revelation. The dark night of the soul does not end with answers. It ends with the recognition that our hunger for truth is greater than our fear of failure, that the universe is stranger than our categories, deeper than our equations, and more mysterious than our imaginations. And so the question remains, hanging in the air like a whisper. If hadrons are not what we thought, what lies beyond them? It begins not with a thunderclap, but with a whisper. A faint signal buried deep in the data, a subtle deviation that should not be there. For decades, the despair surrounding hadrons had weighed heavily, but science is never still. Beneath the fatigue, the machinery of discovery continues to hum. It is in this quiet persistence that the first glimmers of renewal appear. One such glimmer comes from lattice QCD, the computational brute force approach that attempts to simulate the behavior of quarks and gluons locked inside hadrons. For years, the method was too crude, too resource-intensive. But as supercomputers grow in power, as algorithms refine and quantum computing looms on the horizon, lattice QCD begins to produce results of startling precision. Predictions of hadron masses, once approximate, now match experimental measurements with uncanny accuracy. The proton, long an enigma, starts to yield its secrets, not entirely, but enough to restore faith. This is more than a technical triumph. It is a reminder that progress often hides in the margins, advancing one decimal place at a time. The proton may still be a storm of quantum chaos, but for the first time we can sketch its turbulence with clarity. It is as though the fog has lifted just enough to reveal the shape of a mountain, even if its peak remains shrouded. The breakthroughs are not confined to theory. Experiments too begin to uncover tantalizing anomalies. At CERN, at Fermilab, at facilities across the world, detectors pick up signs of exotic hadrons, states that cannot be explained by the simple quark triplets and pairs of the old model. Tetraquarks and pentaquarks, once dismissed as mathematical curiosities, begin to appear in real collisions. These are particles composed of 4 or 5 quarks, bound in configurations that defy the neat categories of baryon and meson. They are fleeting, unstable, gone in a heartbeat, but real nonetheless. Their discovery cracks the illusion of closure. The standard model may be powerful, but it is not complete. The zoo of hadrons is more varied than we imagined, more alive, more chaotic. And with every exotic state discovered, the boundaries of what is possible expand. Physics, once again, is a frontier. Other anomalies deepen the intrigue. Muons, cousins of the electron, behave in magnetic fields in ways that defy the standard model's predictions. Heavy ion collisions produce quark-gluon plasmas that behave almost like perfect liquids, flowing with near-zero viscosity. Inside neutron stars, hadrons may dissolve entirely into strange quark matter, forming objects unlike anything on Earth. Each anomaly is a fissure in the old certainties, a glimpse of something larger. Philosophically, these discoveries change the narrative. The despair of the dark night of the soul was rooted in the fear that we had reached the end, that no further revelations lay beyond. But the anomalies prove otherwise. They show that hadrons are not the end of the story, but the beginning. That reality is deeper, stranger, and richer than the neat diagrams of textbooks suggest. The shift is not only intellectual, it is emotional. Physicists who once feared futility now feel the thrill of exploration return. Conferences buzz with speculation, chalkboards fill with equations that flirt with the impossible. For the first time in years, the word beyond feels real again. Beyond the standard model, beyond the visible, beyond the hadrons we thought we knew. And with this renewal comes a reimagining of what real means. If hadrons can take on so many forms, protons, neutrons, mesons, tetraquarks, pentaquarks, then their reality is not singular but manifold. They are not rigid objects but dynamic possibilities, snapshots of the quantum sea in motion. The breakthrough is not just in data, it is in perspective. Reality is not fixed but fluid, and hadrons are evidence of that flux. But the most profound breakthroughs may come from connections, the weaving together of once separate threads. Cosmology and particle physics, long estranged, find common ground. The study of neutron stars informs our understanding of quark matter. Observations of the early universe shed light on how hadrons formed in the first seconds after the Big Bang. Even dark matter, that ghostly substance beyond our reach, may be linked to the same forces that bind hadrons. String theory too, though controversial, offers strange hope. In its framework, hadrons may be vibrations of strings, their mass and charge the result of deeper harmonics. The ADS/CFT correspondence, a bold mathematical conjecture, suggests that the behavior of strongly coupled particles, like quarks bound in hadrons, can be mapped to the geometry of higher dimensional spaces. If true, this means that the mysteries of hadrons are shadows of an even grander structure. Speculation runs wild. Are protons stable forever, or do they decay over unimaginable timescales? Do exotic hadrons point toward new symmetries in nature? Could the confinement of quarks and gluons be explained not by force but by topology, by the geometry of space itself? Each question sparks another, like sparks in the dark. And yet, through all this, the breakthrough is not certainty, but possibility. For the first time in years, physics feels open-ended again. The despair of limits is replaced by the wonder of horizons. Hadrons, once thought to be understood, are revealed as gateways, portals into realms of matter and energy we have only begun to glimpse. The narrative shifts. No longer are hadrons the prison walls of our theories. They are the keys, exotic states, anomalies, unexpected behaviors. These are not signs of failure, but of opportunity. They tell us that the universe is larger than our categories, richer than our models, stranger than our expectations. And in this strangeness lies the promise of renewal. The breakthrough, then, is not a single discovery but a mood, a new atmosphere in the halls of science. Hope returns. Ambition stirs. Once again, the question of what is real feels alive. And in the glimmer of exotic particles, in the hum of supercomputers, in the whispers of anomalies, the future of physics calls. But the breakthrough is fragile. Every discovery raises more questions. Every anomaly demands explanation. And behind it all, the central mystery remains. If hadrons are not fundamental, if they are but fleeting configurations of a deeper reality, then what is the true fabric of existence? The breakthrough is only a beginning, and so we stand, at once renewed and unsettled, gazing into the unknown. The hadrons have revealed their strangeness, but the ultimate revelation lies ahead. For centuries, physics has walked a narrow road, each step forward illuminating a fragment of reality, yet each revelation shrouding new mysteries in deeper shadow. With hadrons, we believed we had arrived at the solid bedrock of matter, the indivisible bricks of the universe. But in truth, what we found was a hall of mirrors, reflections nested inside reflections. Now, in this final stretch, the mirrors crack, and a new vision begins to take shape. The climax begins with the realization that hadrons, protons, neutrons, mesons, and their exotic kin are not the indivisible anchors of reality, but transient expressions of a deeper dance. They are not the building blocks, but the byproducts, not the foundations, but the ripples on the surface of something far more elusive. Lattice QCD has given us glimpses. Supercomputers simulate the storm inside protons, showing quarks and gluons flashing in and out of existence, bound not by rigidity but by confinement, a force so overwhelming that it refuses to let its prisoners escape. Quarks are never free. Gluons, the carriers of that force, tangle themselves in self-interactions. Hadrons are thus revealed as prisons without doors, paradoxes embodied in matter. And yet paradox is not failure, it is a signpost. The climax arrives when we realize that hadrons force us to abandon the old dream of reductionism, the belief that reality can be broken down into ever smaller, indivisible pieces. The universe is not made of blocks, but of relationships, not of objects, but of interactions. A proton is not a thing, but a storm, a knot of forces, a pattern sustained by the ceaseless tension of its parts. This revelation extends far beyond particle physics. It reshapes philosophy itself. If hadrons, the supposed bedrock of matter, dissolve into processes, then reality itself is process. Existence is not static, but dynamic. Being is becoming. The proton is not real in the way a stone is real. It is real in the way a flame is real, ephemeral, flickering, sustained only so long as energy flows through it. The climax intensifies when we place this insight in the grander cosmic context. In the hearts of stars, hadrons fuse to forge heavier elements, releasing the energy that lights the universe. But within neutron stars, the pressure crushes hadrons out of existence, dissolving them into quark matter, a sea of nearly free quarks that defies our earthbound imagination. Reality, at its most extreme, unravels the very entities we once thought indestructible. Here is the paradox made manifest. Hadrons both sustain and dissolve reality. They are the glue of atoms, the stability of matter, the foundation of chemistry and life. Yet they are also fragile, contingent, destined to collapse under pressure, to decay over eons. Even protons, once thought eternal, may not last forever. If proton decay is real, then the very substance of our bodies and our world is temporary, a fleeting configuration in a cosmos that never ceases to evolve. The climax is also cultural. The question of reality is not confined to laboratories but spills into human meaning. For millennia we have sought permanence, certainty, foundations. Hadrons seem to promise that. But their dissolution teaches us something humbling, that even the most stable things are transient. That change, not stasis, is the true constant of the universe. And yet this is not despair, it is liberation. The climax turns when we realize that the fragility of hadrons mirrors our own fragility, that the transience of matter mirrors the transience of life. And yet, just as hadrons endure through balance, through the interplay of opposing forces, so too does meaning emerge not from permanence, but from tension, from the ceaseless play of energy and form. At the heart of this climax is a choice. Do we cling to the old vision of matter as bricks, foundations, eternal certainties? Or do we embrace the new vision, where reality is woven of flux, where hadrons are not the end, but the beginning, where the true fabric of the universe lies not in particles but in fields, symmetries, perhaps even strings vibrating in hidden dimensions? The choice echoes in every anomaly. Tetraquarks and pentaquarks defy the categories of the old model. Quark-gluon plasmas behave like liquids, not gases, challenging our intuition. Muon anomalies suggest forces beyond what we know. Each is a flare in the dark, illuminating not closure but possibility. The climax is thus both scientific and existential. To study hadrons is to confront the fragility of our certainties. It is to face the abyss of the unknown and to step into it willingly. It is to accept that what we call real may be nothing more than a fleeting configuration, a temporary knot in the fabric of possibility. And yet, in this very fragility lies wonder. For hadrons, in all their instability, sustain the cosmos we know. They are fragile storms, but storms that endure for billions of years, long enough for stars to shine, for life to emerge, for consciousness to awaken and ask these questions. So the climax ends not in despair, but in awe. The hadron is not the end of inquiry, but its beginning. Its reality is not in its permanence, but in its becoming. And as we glimpse beyond it, into the realms of quantum fields and possible new forces, we are reminded of the most profound truth of all, that reality is stranger, deeper, and more magnificent than we can ever imagine. The climax has been reached. The hadrons have spoken, not with certainty but with paradox, not with answers but with questions. And in those questions lies the true grandeur of science. For if hadrons dissolve into storms, then so too do we. And yet, in the storm there is meaning, there is beauty, there is truth, but the journey is not yet over. For even in this climax, one mystery remains. If hadrons are not the foundation, what lies beneath them? What deeper reality sustains the storms? That question, haunting, unanswerable, yet irresistible, is what pulls us forward into the finale. We began with solidity, with the comfortable illusion that matter is made of bricks, neatly stacked, unchanging, eternal. We saw hadrons as those bricks, protons, neutrons, the timeless anchors of atoms, the very stuff of ourselves. But after a journey through paradox and revelation, we arrive at a transformed vision. Hadrons are not the immutable stones of creation, but the storms and swirls of a universe that is dynamic to its core. The resolution is not to deny reality, but to redefine it. For if hadrons are storms, then their reality is no less profound. They endure, not by being fixed, but by balancing. They exist, not as objects but as patterns, shaped by the relentless push and pull of quarks and gluons, bound by the invisible grip of confinement. The proton is a process, the neutron a rhythm, the meson a pulse in the deep structure of existence. This new understanding is the boon we bring back from the journey. It teaches us that reality is not about permanence but about persistence, not about solidity but about stability through change. A hadron is real because it persists, because its storm holds long enough to shape atoms, to fuel stars, to sustain life. It is real because it endures across billions of years, even as its innermost structure remains a blur of ceaseless motion. The resolution deepens when we reflect on what hadrons mean for the cosmos at large. Without them, there would be no nuclei, no chemistry, no stars. Their stability underpins everything familiar, from the beating of a human heart to the burning of the sun. Yet even this stability is conditional. In the crushing depths of neutron stars, hadrons yield, dissolving into quark matter. In the far future, protons may decay, erasing the very scaffolding of ordinary matter. The reality of hadrons is thus a temporary gift, one phase in the ceaseless unfolding of the universe. This perspective does not diminish their importance. On the contrary, it magnifies it. To know that our world rests on storms sustained by balance is to glimpse the fragility and the grandeur of existence. It reminds us that life itself is a similar storm, fragile yet enduring, balanced on the knife edge of entropy. Hadrons are not illusions, they are lessons. And the lesson is that reality is emergent. Just as hadrons emerge from the interplay of quarks and gluons, so too do atoms emerge from hadrons, molecules from atoms, life from molecules, and consciousness from life. Each level is real, not because it is fundamental, but because it persists, because it acts, because it shapes the world. The resolution, then, is to embrace reality as layered, relational, emergent. to abandon the dream of ultimate bricks, and instead to see reality as a symphony of processes, each one giving rise to the next. This resolution echoes in philosophy as well. The old metaphors of being must yield to metaphors of becoming. To exist is to endure in the flux, to balance against dissolution. A proton is not less real because it is emergent. It is more real because it reveals the truth of existence, that to be is to be dynamic, to be transient yet enduring, to be a storm that holds its shape across the tides of time. The resolution also reframes science itself. We often think of science as a quest for final answers, for ultimate foundations. But the Hadron teaches us that the search is not for an end, but for a horizon that always recedes. Each discovery deepens the mystery, each equation reveals new paradoxes. The reality of hadrons is a reminder that knowledge itself is emergent, that truth is not a fixed point but a journey without end. And yet this is not despair, it is wonder. The resolution is awe, not closure. For hadrons are enough to sustain the universe we know, enough to fuel the stars, enough to carry the weight of life and thought. Their storms have lasted for billions of years, long enough for us to awaken within them and ask these questions. That is reality enough.
Still, the resolution carries a haunting note. For if protons can decay, then all that we know is temporary. The stars will die, the atoms will dissolve, the hadrons themselves will fade into the cold silence of the far future. This truth is both terrifying and liberating. It reminds us that meaning cannot be found in permanence, but only in the present, in the storm sustained for now. The boon of understanding is thus twofold. Scientifically, it is the realization that hadrons are not bricks, but processes, not foundations, but patterns of balance. Philosophically, it is the realization that reality itself is emergent, that existence is flux, that meaning is found not in what lasts forever, but in what endures long enough to matter.
The resolution reaches its peak when we return to the image of the human hand on the table, the same image with which we began. But now the perspective has shifted. What once seemed solid is revealed as storm, what once seemed permanent is revealed as transient. And yet in that revelation there is no loss, only wonder. For to know that your hand, your body, your world is made of storms sustained across cosmic time is to see reality anew, fragile, fleeting, but magnificent beyond measure. And in that new vision lies transformation. The Hadron has taught us that reality is not about things but about patterns, not about permanence but about persistence, not about final answers but about ceaseless becoming. This is the boon we carry forward, a new way of seeing, a new way of being, a new way of understanding what it means to be real. But even as the resolution brings closure, one last question lingers, as it always must in the deepest journeys of thought. If hadrons are storms, sustained by balance, what greater storms might exist beyond them? What deeper patterns might lie beneath the ones we now know? The resolution leaves us transformed, but also haunted, compelled to press on, to keep asking, to keep seeking. And so we stand at the threshold of the finale, where the journey comes full circle, and we confront not only the hadron but ourselves. For if hadrons are storms, then so are we. And in that recognition lies the final truth of the story. The journey ends where it began, with a hand resting quietly on a table. To the eye, it is solid, dependable, permanent. But now we know better. We know that beneath the skin, beneath the atoms, beneath even the protons and neutrons, lies a seething storm, a storm of quarks and gluons, bound so tightly that they can never be freed, forever swirling in an endless dance. Hadrons, not bricks of eternity, but patterns of balance, storms given form. What does it mean to live in such a universe? It means that solidity is an illusion, but not a meaningless one. The table holds, the hand rests, the world persists, because patterns endure. The proton may not be a thing in the old sense of the word, but its storm has lasted billions of years, long enough for stars to shine, for Earth to form, for life to emerge, for us to awaken. Reality does not need to be eternal to be real. It only needs to endure long enough to matter. The epilogue is not about closure, but about perspective. Hadrons have shown us that reality is layered, emergent, dynamic, that permanence is an illusion, but persistence is enough, that the universe is not built of blocks, but of relationships, symmetries, flows, and that within those flows meaning is not lost, but found. There is a humility in this vision. To know that even the proton, the symbol of stability, the heart of atoms, may one day decay, is to confront the fragility of all things. But there is also a grandeur in it, for fragility does not mean insignificance. Fragility means urgency, beauty, wonder. To know that we too are storms, transient, balanced, fleeting, is not to diminish us, but to place us in harmony with the universe itself. The storm that is a hadron is not so different from the storm that is a life, or a mind, or a civilization. Each is fragile. Each is fleeting. And yet each is real, not because it lasts forever, but because it endures for a time, shaping the world, leaving its mark. So, as we close this journey, we return to the question with which we began. Are hadrons even real? The answer is not simple. They are not real as immutable bricks. They are not real as unchanging things, but they are real as patterns, as processes, as storms of becoming. They are real because without them, there is no world, no life, no us. They are real enough to carry the universe, to light the stars, to sustain the fragile miracle of consciousness. The final truth is that reality itself may be nothing but storms. Storms of particles, storms of galaxies, storms of thought. And we, fleeting as we are part of that storm. The hand rests on the table, the world holds, the storm continues, and the question lingers, as it always must. If even hadrons are storms, what lies beyond them in the deeper patterns we have yet to see? Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.